Alright, so here we go with the first homework review of the spring 2016 semester. We're trying to do these every week to go over things from the previous homework assignment that we may need to clarify a little bit. You know, things that we had trouble with when we did the problems, things that I probably should have taught you better in the first place, and so on. So if you have any requests for these videos, I guess you can send them to me during the week. I'll be doing these every Monday. But generally what I'll do is just go through the homework, look at the results of each problem individually and try to find the ones that we struggle with the most and sort of review those topics, review those problems specifically. So one thing I got a lot of questions about and that we had some difficulty with on the homework was the implications of the Rutherford gold foil experiment and what it tells us about the atom or what it doesn't tell us also. So remember that the Rutherford gold foil experiment, he shot alpha particles at a thin piece of gold foil and found that many of those particles were deflected at very high angles. So this told us a few things about the atom that were previously unknown. And the main thing was that this resulted in the discovery of the nucleus. So before this, remember the plum pudding model was sort of all the rage. And in that model, the positive charge was spread around the atom evenly and intermingling with the electrons. So the discovery of the nucleus, and another big implication of this is that the atom is mostly empty space. Okay, so the nucleus is tiny compared to the size of the atom. The electrons themselves, while they're moving around a lot and occupying a lot of available space, they themselves are also tiny too. So really at any given time, if you take a snapshot of an atom, it's going to mostly be empty space. Now, a couple things the Rutherford gold foil experiment doesn't tell us. One is that it said nothing about neutrons. The discovery of neutrons came later. We didn't really get into details of that because it's a lot of nuclear physics that are beyond the scope of this course. But Rutherford's experiment didn't directly prove the existence of neutrons. That came much later. So we know that all the positive charge and most of the mass for the atom is localized in the nucleus now, but neutrons, nothing directly said about those with this experiment. And then also nothing really quantitative about the mass of any of the subatomic particles. Those could be measured separately, but we don't know exactly what the mass of the proton is from this experiment or the mass of the nucleus itself. We just know that it exists and that most of the mass for the atom is there. So this was not a totally quantitative experiment. It was more qualitative. It was just looking at the angles of reflection of these alpha particles, and that sort of led to the belief, which is largely believed to be correct, that there's a very dense nucleus at the center of atoms, something that wasn't known before. So that's what the gold foil experiment tells us, and nothing more than that. So then there's one problem on the homework assignment, and these ones are always challenging just in terms of how the problem is set up. Which of the following statements is true? And you have three different statements here, and you also have answer choices that say two of them are true or that all of them are false. So that sort of leads to just you have to really know the material front and back. And for these conceptual problems, it's really trying to understand it at different levels and understand it worded in different ways so that you can approach the problem no matter what we ask you about it. If it's not exactly word for word from the book or from the notes. All right. So which of the following statements is true? Ions are formed by adding or removing protons or electrons. Okay, so remember that A is false because we can only form ions by removing electrons. So only electrons are added or removed when we form ions. I don't think any of you picked this one, or very few of you picked these ones. But the answer choice that was popular was choice B. Many of you thought that this was also false. So scientists believe that solids are mostly open space. Now, we didn't talk a lot about the states of matter in lecture, but a solid is a state of matter where the atoms are themselves packed very closely together. So this may lead you to believe that there's very little empty space in a solid. But remember that the individual atoms themselves are mostly open space, and that's what the Rutherford gold foil experiment told us that I talked about previously. So many of you, I think, based on your answer choices, thought that B was also false, but this one is in fact true, because atoms themselves are mostly open space. So there's not a lot of space in between the atoms in a solid, but inside each individual atom is a lot of open space. Okay, so I think that's where the confusion came in, is remembering that key point of the Rutherford experiment, which is that atoms are mostly empty space. And then choice C, very few of you picked this one, but this is also false. Heating water with a Bunsen burner results in a 2-to-1 mixture of hydrogen and oxygen gases. Heating in the case of water especially, heating is just a physical change. You will boil the water, make water vapor, but this is only going to bring about a physical change. You can't just break down a substance into its elements by heating it, at least not generally weaking. You can sometimes, but not in the case of water. So here we're talking about a physical change. And again, very few of you picked that answer choice. But I think the one that was confusing to most people was B. We have to realize that that's true because of what the gold foil experiment tells us, which means that choice B is the correct answer for this problem. Now, I guess, but before I move on, another set of questions that many of you got wrong, actually the ones that were the most frequently missed, had to do with Avogadro's number, which is this concept of a mole and how many particles are in a mole. I didn't cover that in class yet, so this is something that sort of snuck through and was here from a different version of the homework. So don't worry about the mole just yet. I'll make sure that there's no test questions on it until we've covered it. I apologize that there's a couple homework questions that involve the mole that we hadn't really covered yet. So those ones don't worry about, but the ones that I'm going through in this presentation are going to be ones that you should be pretty familiar with at this point that we still had a little bit of trouble with. Now another question that some of us struggle with was the mass laws presented at the atomic level. So this is a holdover from the previous version of the textbook, which loved to show these sort of atomic molecular pictures of things and ask you conceptual questions about them. So here we have a collection of atoms, and they're combining in different ways, and we want to know which mass laws are illustrated in the figure below. Now we think about the three mass laws. So the first one is conservation of mass. And so when we're looking at an atomic level picture, remember that the conservation of mass law tells us that atoms are neither created or destroyed. So if we look at the left side, which is what we call the reactant side of this picture, and we look at the right side, which is the product side, we should have the same number of atoms in each side, in the same number of each type of atom, if the conservation of mass is upheld. So if we look at purple, let's do it for the left side first. Okay, so on the left side, if we count the number of atoms of each type there are, we don't know what exactly these are, they're just different colors, but we have 1, 2, 3, 4, 5, 6, 7 purples. And then on the green side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 greens. Alright, so 16 total atoms, 7 of one type, 9 of the other. If we go to the right side, if we count the number of atoms of each type, the purple we have 1, 2, 3, 4, 5, 6, 7. So some of the purples have now been combined with greens to form molecules, to form compounds, but there's still 7 total purple atoms, and then green 1, 2, 3, 4, 5, 6, 7, 8, 9. We also have 9 green. Okay, so the number of each type of atoms is the same on both sides, so this demonstrates the law of conservation of mass. Now we think about another mass law, which is definite composition. And definite composition deals with the composition of a compound, which is again formed by some ratio of atoms or elements combining to form those compounds. We want to see, is the law of definite composition upheld here? That would require that all of the compounds of one type have the same composition. So if we look at the right side of our equation, the right side of our picture here, we have our molecules that are formed. Those are the ones that have 2 different kinds of atoms in them. We have the molecules all have 1 purple and 2 green. Okay, so every single molecule that's formed, all of this compound that's formed from the purple and green elements combining, they all have the same composition, 1 purple to 2 green. So the law of definite composition is upheld. Now the one that's the most confusing of the laws and hardest to conceptualize is multiple proportions. Now we can talk a little bit more about multiple proportions and what exactly it means, but the point is, if you're going to demonstrate the law of multiple proportions, you need to have 2 or more compounds with the same elements. Okay, so that's what the law of multiple proportion tells us. It's relationships between multiple compounds that form from the same set of elements. Alright, so if we look at that situation here, that we don't have that. Okay, as I said in the previous definite composition discussion, we only have compounds that have 1 purple and 2 green. That's the only compound that forms from those 2 elements. So this picture here does not demonstrate multiple proportions. There's only one type of compound formed from the 2 elements, so we don't have that here. So the mass laws that are illustrated are conservation of mass and definite composition by this picture here. Okay, so these are the three mass laws, and remember, for multiple proportions, we have to have two different compounds formed from the same elements. And on a molecular level, multiple proportions would be, for example, if we had two different compounds like this, with, let's say, red and blue here as I'm drawing. Okay, if we had molecules that look like this and molecules that look like this in our picture, this would be an example of multiple proportions. You have two different molecules with the same elements but in different ratios, and that's what multiple proportions tells us. As a mass law, it deals with masses of elements, but we can also think about it on the atomic or molecular level, which is that two different atoms combining in two different ratios to form molecules. Okay, so we want to make sure we're clear on that, on the differences between those mass laws. And these molecular level pictures, they do come up a bit because, again, they were popular in the old textbook, and it is helpful to think of these mass laws on the atomic level because that's what the atomic theory does for us. It describes the mass laws at the atomic level and why they're true. All right, now finally, one other problem that I want to go over deals with subatomic particles. So we had a little bit of trouble with this one. The sum of the number of neutrons and electrons in the 80 As3- ions. That's arsenate is what it's called, and it has a 3- charge. So again, for this one, it's probably best to approach it separately. So we need to know the number of neutrons and the number of electrons and add them together. Now, to do this, we also need the number of protons, which is not directly given to us. And that one we can get directly from the periodic table. So if we search through our periodic table, the number of protons is the atomic number, which is the number listed above that symbol on the periodic table. So if we go to the periodic table and find arsenic, As is atomic number 33, so there's 33 protons. That's the atomic number. Alright, and you will always have the periodic table with you on your exams, so get used to using it and get used to knowing what some of those different things mean. So number of protons is 33, that comes off the periodic table. So the number of neutrons is the mass number 80. So this 80 here in the formula or in the symbol, that tells us how many protons plus neutrons there are. So the number of neutrons plus the number of protons is this number that we call A here in the formula, which is the mass number. Sorry. Okay, so that mass number A, which is the superscript, is the number of protons plus neutrons, which means the number of neutrons in arsenic 80 is going to be 80 minus 33, which is the number of protons, and that gives us 47. Okay, so there are 47 neutrons. Now we need the number of electrons. Now the number of electrons in a neutral atom is the number of protons, but we have 3 negative charges, so we have to add 3 to that. Okay, so arsenic 3- has 33 protons to balance out the positive charge in the nucleus. And there's 33 protons, which are balanced out by 33 electrons, but then we have an additional 3 electrons that give it the -3 charge overall. So we have 36 electrons. And so what that means is that the number of neutrons plus electrons, which is what this problem asks for, is 47 plus 36, which is 83. Alright, so we have 83 neutrons plus electrons in this ion. Alright, so again, do them separately and then add them together at the end. There's no shortcut way to find the sum of neutrons and electrons. We can find the number of neutrons from the mass number. The number of electrons comes from the number of protons in the nucleus plus the negative charge added on, or the positive charge subtracted out if it was a positive ion. Alright, and then finally, last thing about subatomic particles. This one caused some confusion just because of a definition, being precise about our definitions here. So when we have these atomic symbols here, which are A, X, Z, so remember that we're asked for what the value of A is here. So what does this mean? So A is what we call the mass number, and this is just the number of protons plus neutrons. Now, many of you got this right, but many of you also thought that this was the atomic mass. So the mass number is not the same thing as atomic mass. Alright, so they're not the same thing. We haven't really learned about atomic mass yet, but atomic mass is related to the mass number, but it's a weighted average of all of the isotope masses. Here the mass number is just the number of protons plus the number of neutrons for a specific isotope. So mass number refers to one isotope, and the atomic mass is all isotopes. Furthermore, another subtle point that's not that important now, but the mass number is not exactly equal to the mass of that isotope anyway, because remember we have some mass loss when neutrons and protons combine to form a nucleus. That's from E equals mc squared. So the atomic mass is all isotopes averaged together. The atomic mass is the mass number is one isotope, but yet at the same time, we have to be aware of those differences. And the atomic mass is something we'll talk in more detail about. I believe it's sometime in chapter 4 or 5. So still, a few chapters away for us for atomic mass. But right now, we should know the mass number, and that has this precise definition: number of protons plus number of neutrons, and it refers to one specific isotope of that element. Okay, so each isotope has its own mass number. So there is a relationship, but we have to make sure we're aware of the differences as well. Alright, so that wraps up this first attempt at a homework review video. I hope some of you find this helpful. And again, if you have different format you want me to follow on these, specific requests for material that I should cover in one of these, please just let me know. I'm open to suggestions, and I want to do this as a way to be as helpful to you as possible and give you a chance outside of class to review things that we're not going to have time to go over them again in class because this is old material now, but hopefully we can use these videos as a way to review some things and make sure we're sharp on everything before we move forward into the new material. Alright, thank you. I will see you again soon.